And I need to share the screen. So I think you can see that, right, Kiana? The screen?
Yes.
Okay, good. All right. So now we're down to 20%. know a lot of people watch the show though on the website or on La Lima. So welcome students that are seeing this in the future or reviewing. So we're on to our last topic. I'll talk about nuclear chemistry today and tomorrow, and then I'll go through and I'll look through your guys' homework and see where you guys are lacking. Is there any topic you want me to go over again? I mean, this is just review for the final. Typically, the topic that students want to go over the most is determining the rate law from data back in the kinetics chapter. And the other thing that students don't like is balancing oxidation reduction reactions. That's probably the second least favorite thing. But I was also going to focus on your homework. Is there any topic that you want to go over? Okay. If you think of anything, or those listening to this, drop me an email and I can always put that in. So, and if you're wondering why we have extra time, it's because the tests are done online. And I'm surprised. I thought this class was not going to make it face-to-face, because if you remember in the beginning of the semester, we started off as we were online. Was it like 3 weeks? I think we were just doing Zoom, or was just, I was doing it in my living room. And then that was the worst. I was even thinking about this. I'm like, that was the worst start of the semester I have ever experienced in my 16 years of teaching. Was it 16 years? Was it 15 years? Let me think. That's 16 years. 16 years of teaching, and that's the worst start of the semester I've ever experienced. And I mean, it was just nuts. And I'm glad we made it so far. I'm happy to do face-to-face, and hopefully the pandemic is over now. It seems like things are gearing towards that, and all we got to worry about now is World War III, right? So all right, so our final topic is on nuclear chemistry, and it's actually, I started out as a nuclear scientist in graduate school, and I switched to chemistry. I was specifically in nuclear chemistry, but I switched to physical chemistry, and although nuclear chemistry is considered physical chemistry, but I switched to lasers partially because to be a nuclear scientist, it really kind of limits your job prospects. So I was thinking more on a practical note, and I like science in general. I mean, of course, I'm a chemist, and it's just, I'm just one of those people that just likes everything. I think everything's cool, kind of thing. And I'm like, well, what do I study? I'm like, well, I like geology. I like nuclear stuff. I like stars, all this stuff I could study. And it's like, well, chemistry is kind of a good thing to look at everything. So actually, as you know, I started off as a chemical engineer, an undergrad. And then in grad school, or in undergrad, I'm like, I don't want to be an engineer anymore. Like, oh, I'll be a scientist. And like, well, chemical engineer, chemistry wasn't a big jump, and then I started off doing nuclear stuff, and I'm like, I don't know because if a lot of people that do this, you have to work in a particle accelerator or with nuclear stuff like radioactive materials, and that the skill sets you learn from there, they are not as applicable in other places. So I moved over to study lasers, and but then now I'm a teacher, so here I am, the chemist over at Kapiolani, not Kapiolani, Kauai, so the other K. Kauai Community College is a nuclear scientist as well. So well, he also teaches chemistry and physics. So, but his background's in nuclear science. So I just started off in it. He's much more knowledgeable than I am, but I know quite a bit about this though as well. So, but for nuclear chemistry, If you think of chemistry, like one of the ways I think of just plain old chemistry, I think of it as like the study of electrons. I mean, so when all the stuff that happens, it's the electrons that are doing all the work, right? So when chemical reactions happen, what happens? Well, the electrons move around and you have charged particles. Why are they charged? Well, either the electrons move from one atom to the other, or they move to one side of the atom and you have a polar molecule, and then you have Coulombic stuff. So, and it's so really chemistry is all, like I said, is all electrons flowing where they are, where they're not, and how they move. And another secret though, nuclear chemistry sounds really scary. Nuclear science is so much easier than chemistry because of the electron. So a proton or neutron has about 2,000 times as much mass as an electron. And it depends, I'm saying about, because it depends on the environment. So the protons and neutrons masses change depending on what the environment they're in. And it's a little less than 2,000. And so all the things with electrons too. So when we have orbitals, S, P, D, E, F orbitals, right, for electrons, there are orbitals also for protons and neutrons. So in the nucleus, just like electrons, when you have the building up principle, the Aufbau principle, right, when you have the levels, the 1s, 2s, 3s, 2p, and then, you have like Hund's rule. You have that too with protons and neutrons. Protons and neutrons are also fermions. They're just like electrons. Electrons are also fermions. So they have orbitals and they have wave functions. And so everything is very, very similar. And the difference though is that the energy levels are so huge in nuclear chemistry. The spacing between the energy levels is just gigantic. And because of that, the energy levels in a nucleus, they don't interact with each other. Whereas electrons interact with each other. So the math is so much easier for nuclear chemistry. For chemistry, the math, like if you study quantum mechanics, because electrons and protons and neutrons too, but electrons, they're a lot like waves. I mean, they have wave particle duality. And when you have two energy levels that are close together, like one is slightly higher than the other, these energy levels, if you have electrons populated in both, they can interact and they act like waves, and you have interference, and then you have crazy things happen. For protons and neutrons, energy levels are just huge. So if this level is populated, this is populated, they just don't interact. So it's almost like they're individual energy levels, and it makes the math just so much easier. So much easier. So, and let me back up. Probably one of the words that we think of nuclear, we think of radioactive. So what is radioactive? It means unstable, but I'll back up even more. So if you remember back, if you had me for Gen Chem 1, I said, well, you remember the four fundamental forces? Do you guys remember the four fundamental forces? And some people think they're 3 and some people think they're 5. It's a conflict. But do you guys remember what the four fundamental forces? Do you remember any of the forces? Weak force, that's one of them, yes. Strong force is another. Oh wow, the complicated ones. What about the other ones? Electrostatic, anything else? You can't think of any force? Yes, gravity. I'm jumping up and down. Oh, you did it backwards. Well, I guess the third force is the weak force. So yes, way to go. Congratulations. So gravity is the weakest force. So, and then there's electrostatic, which is chemistry, is basically a study of that. Then the weak force, what is the weak force? Protons and neutrons are made of smaller particles called quarks. And what binds the quarks together to form protons and neutrons is the weak force. It turns out that the weak force actually is electrostatic. So you could argue that there are 3 fundamental forces, because the weak force is not a different force. We also didn't mention one of the forces. Dark energy is the last one that maybe we don't know. for the latest data that we can tell, the universe, so we think that well, 14 billion years ago, thereabouts, 13.8 billion years ago, there was a massive expansion event, also known as the Big Bang. And the universe has been expanding since then. And the data suggests now that the universe is expanding faster. So as time is increasing, the universe is actually accelerating as it's moving apart. And we don't know why it's accelerating, so we just call it the dark energy. So dark energy. So whenever you hear the word dark, it means we don't know what's there. So dark matter. So dark matter, for instance, is we see things move and they respond to gravity, but we don't see the matter. We know that the gravity is there, but we don't know where the mass is. So we just say it's dark matter. And so the universe is accelerating and it takes energy. So force is mass times acceleration. So there's a force being pushed on the universe causing it to accelerate, and a force times a distance, that's energy. So we have this source of energy, we don't know what it is, so we call it dark energy. So maybe you could argue that there's 5 fundamental forces, right? So gravity, electrostatic, nuclear weak, nuclear strong, and then dark energy. So, but we don't know what dark energy is, so most people leave it out. But then go back to the strong force. So what is the strong force? Well, if you look at a nucleus is made of protons and neutrons. Protons have a positive charge, neutrons have no charge. So in the nucleus is tiny. There's a lot of matter. So by a factor of about 2,000. So about 2,000 times of the mass of the atom is in the nucleus. So that's a pretty strong concentration of matter in a small area. And in that small area, you have protons that are positively charged. So in a really small, dense area, you have a bunch of positive charge. Positive charges repel each other. So you have a huge amount of electrostatic repulsion inside the nucleus of an atom. And so there needs to be a different force, and we call it the strong force or nuclear strong force, that is stronger than the electrostatic forces, which holds the nucleus together. So that's the idea of the strong force. So the strong force is a really strong force, stronger than the electrostatic force. It's also a very short distance. So it only exists within the nucleus or slightly surrounding the nucleus. So it's a really strong force and it binds the nucleus together. And so that's the reason why the nucleus has that large amount of positive charge in such a small area. And that's the nuclear strong force allows that. Now, protons and neutrons both can feel the strong force. Electrons don't feel it. So it's another thing that's weird about the nuclear strong force is that some particles feel it, some particles don't. So protons and neutrons feel it, electrons don't. There's other particles. So there's something called a pion. A pion is when you have a quark and an antiquark together, and they form that has the nuclear strong force. Then there's muons. Muons are more or less like heavy electrons. So they're similar, they're fermions, just like electrons, same charge, but much more massive. They do not experience the strong force. So these are, and why, and we don't know, or maybe someone knows, I don't know. So there are some weird things. And I did mention like antiparticles. So if you're wondering how antimatter works, so we are made of matter, okay? And if I guess you missed, we had some discussions before about about electricity and magnetism. And this is not in the class, and I'm not gonna test you on it. But like, for instance, we use the right-handed rule, and we assign the right-handed rule for matter. So this is my right hand, and if current is flowing, so if we have a wire and current is flowing, we say that the magnetic field curls this way. So with the curl of my right hand around a wire. So if we have electrons flowing, it would be electrons, but the electrons would flow this way, but the current flows this way. So if the current flows this way, the magnetic field is this way. If you had positrons flowing through an anti-wire or whatever, like a anti-copper wire or something like that, it would go the other way. So if you had your current antimatter flow this way through an anti-wire, the magnetic field would flow this way. And that's with antimatter. So antimatter seems to be nearly identical. It's almost always identical with very few exceptions to matter, but it has opposite charge and opposite headness of spin, meaning that the magnetic field twists the other way. So matter twists one way and we assign the counterclockwise direction. Antimatter is the other direction. So that's matter and antimatter. And when matter and antimatter meet each other, they annihilate each other and turn into energy. So that's another interesting thing about matter and antimatter. And why there's able to have things like pions that are made of matter and antimatter, I don't know. It's kind of cool. I always thought it was kind of cool that they exist. I mean, they don't exist for very long, but they do exist. So we do study antimatter. Well, we as in collective human society, they do it at the LHC, the Large Hadron Collider in Europe. So they make some antimatter there, and they study properties of antimatter among other things. So, but okay, so let me go back to the strong force. So as mentioned before, we have strong force because we have this positive nucleus and lots of positive charge in the small area pushed close together. So we have the strong force. It's stronger than the electrostatic repulsion, but it's not. You can get the repulsion can be so strong though that the nucleus of the atom becomes unstable. So I mentioned before, neutrons also have the strong force. So protons and neutrons have the strong force. And later on, I'll show you a graph. As you get higher up in the elements, as the nucleus becomes more positive, the nuclei have more neutrons. And it's because the neutrons need to use, it's kind of a glue that that holds the atoms together. But then you get to a point where the atoms are no longer stable. Or they're more stable in another form in the case of too few neutrons. So in that case, the atom is known as radioactive. And where did the term radioactive come from? They found out that so when we originally studied uranium, so we knew about radioactivity. We knew it was kind of weird. Like we know there's some elements that give off rays. We originally called them uranic waves for uranium. Like uranium puts off these uranic waves, and then among other things, we found out like, you know what? These are radio waves, and I mean there are radio waves given off, but it's very, very weak. But they could find out like, oh, there's a little bit of radio waves here. I mean, of course, it's mostly gamma, but the radio waves coming off, they're like, all right, well, we'll call it, since this generates radio waves, we'll call it radioactive. I mean, I guess gamma active is more appropriate or something like that, but that's the term radioactive came from. And what it really means, like I said, it means unstable. So it means that the nucleon, the nuclei is just unstable and it falls apart. And whenever, just like electrons, right? When you have electrons and you jump energy levels, they emit visible light. So whenever there's a jump in energy levels in nuclei, they emit gamma rays. So, and it's real easy to find radioactive things. It's real easy to measure things like concentration. So, because there's a directly proportional amount of radioactivity to concentration. So right away, you know what the concentration of your solution is if you have a radiation detector. So like if you work with plutonium or something like that, you have in solution, it's easy to like right away. It's very easy to figure out how concentrated it is. Very, very fast using the radioactivity. But okay, and I'm kind of should go down my list. Let's see here. I already mentioned the first point, and yeah, and I know we don't study that much quantum mechanics, but you like hopefully I've had you start thinking about electrons, this kind of fuzzy gas that moves around and has different shapes and flows and ebbs, and the same thing is true for protons and neutrons, except they have a very different. Well, the energy levels are so high that there's not this interaction. They don't really, other than the electrostatic force, the interaction is very different. Also, the density structure, if you look at like, if you look at like charge, I know what a term for charge would be. Charge versus distance in the nucleus. It kind of looks like this. It's like, whereas an electron, so I'll do like yellow for the nucleus, the charge is actually, it's kind of more or less kind of like that, if you can see it. Or maybe, I know it's kind of more bumpy. So you'd have like, it's kind of like that for, although it's not the same distance scale, it'll be much longer distance for the for an electron. But right, you get a lot more electron density closer to the nucleus in an atom, whereas the charge density of the nucleus of an atom, it's more or less constant. It's not constant. It's kind of wavy, and then it kind of tails off fairly quickly at the end. But the charge density inside the nucleus is much different than the electron charge density in an atom. So I mean, there are some differences. So, but this all stuff, I mean, this is very high level, but I think it's kind of cool. So I'm teaching it. Wow, I can teach what I want. So, okay. And so let's talk about what you do have to know. You do have to know nuclear equations. So all this stuff, the background, what the heck? Nope, I don't want that. There we go. All the background I was given on this stuff, you don't really have to know it, but I'm trying to inspire you to study more cool science, because science is awesome. But what do you have to know for this class? You have to know how to solve nuclear equations, and the top and bottom numbers on both sides have to equal. So when we do nuclear equations. So also review. So this is uranium-238, and uranium has, so you define elements by the number of protons. An atom of uranium, every single atom of uranium has 92 protons. That's what it means. And 92 protons, the bottom number, this is the atomic number. So this is the atomic number. The top number is the mass number. The mass number is the number of protons plus the number of neutrons. And if you notice also how I've written protons, protons have one mass units, and it's close to AMU, atomic mass units. And so protons have one charge and one mass unit, and the charge refers to it's positive 1.6 times 10 to the minus 19 coulombs. That's the charge of one proton. It's also the opposite charge of an electron. Electron has the same charge but opposite. So, but we just pick the protons to be positively charged. So it's just they have to be, the negative charge means nothing. It just means it's opposite to the proton's charge. So so the number of charges is, like I said, the number of units of 1.6 times 10 to the minus 19 coulombs. And then the top number, the mass number, it's the number of mass units that's close to 2,000 times that of an electron. So I don't know the mass of the AMU off the top of my head. AMU, atomic mass unit, is actually it's derived from carbon 12. So a nucleus of carbon-12 has 12 atomic mass units, AMU, and then so 1/12 the mass of a carbon-12 nucleus is the basis for it. And depending on the different circumstance, I'll cover the charts later, protons and neutrons have different masses depending on their environments. So, but for the nuclear equations, we just have the number of protons, number of neutrons, that's the total mass of that. So you can see protons are listed as 1, 1, and then neutrons have 0 charge, but more or less 1 AMU mass. So let's look at alpha decay, and so we talk about the different types of radiation. So the different decay particles that we have, well, if you want to consider gamma rays, which is actually energy, but we have alpha, beta, and gamma, and we use the lowercase for that. So, well, I guess for alpha, I guess we say it's alpha. So, but the Greek alphabet, I know we don't really have fraternities here. I was in fraternity, I was Sigma Chi, and one of the things that all Greek fraternities have to learn, we have to learn the Greek alphabet. And the Greek alphabet has capital letters and lowercase letters, just like we do in English. And there's capital alpha, capital beta, lower beta, capital gamma, and lower gamma. And so we use the lowercase ones to describe the radioactivity. And an alpha particle is a helium nucleus. So, and here is a balanced nuclear equation. And so uranium decays via alpha decay. Well, uranium-238. You can have other types of decay routes, but the uranium-238, its primary way of decaying is by alpha decay. So you have here, you have the parent nuclide. So you start off with the parent, and then all the decay products, they're called daughters. So the parents in nuclear decay, we only have daughters. And so you have a daughter nuclide, and then other things. And for uranium, you have an alpha particle, which is a helium nucleus, and a gamma ray. And if you look at the math, so you have the top line here. So 238, so you can look at it this way. 238 equals 234 plus 4 plus 0. Maybe I should use a different color. I'll change to green. 234 plus 4 plus 0. Right, 234 plus 4 is 238, and plus 0 is still 238. So you can see the top numbers equal, and let's look at the bottom numbers. So, and the charge on the bottom numbers, 92 equals 90 plus 2 plus 0. So this is a balanced nuclear equation. So, and you can see nuclear equations are pretty easy to balance. So, and they're pretty easy also because they tend to only go in a certain direction. So meaning if it says alpha decay, you know you're losing 2 charges and 4 mass numbers. So that's your alpha decay there. And so also with any nuclear transition, whenever you have a nuclear transition, there's always a gamma ray released. And that gamma ray, and it's real easy to find that gamma ray. Really easy to find it. And so detecting radioactivity is very simple. So, but let's talk about the different types of decay. There's alpha decay, and alpha decay is a helium nucleus. Beta decay, which we'll cover soon, this is an electron. So beta decay, an electron pops off, and then gamma ray, it's light. Well, it's not light, it's electromagnetic radiation. It's like very energetic light. So when it comes to penetrating power, so how far radiation will go, alpha goes the least. So if you have an alpha source, it's really easy to stop an alpha source. Your skin could stop it. Your t-shirt could stop it. It's a piece of paper could stop it. It's the penetrating power of alpha is not very far. Beta can go a little further. Beta can go a few inches. So the beta decay, well, beta sources, you want to have a little more protection for them, but like your eyes are a little more sensitive. Depends on how far away. It can go through some of your skin, and it can give you a light radiation burn, like a sunburn, like a first-degree burn. But it's rare that you'd have that much beta particles. But your eyes are fairly sensitive, especially in forming cataracts. So you can stop beta particles with a like just plain old glasses, just like, safety glasses would stop beta particles, and your eyes would be safe then. And then you could maybe put on, like a couple layers of clothing, like have your normal clothes on and then a lab coat on, and you'll be pretty, and a pair of gloves or 2 pairs of gloves. Whenever you work with radiation, it's very frequent you wear 2 pairs of gloves, and you change them frequently as well. So that's usually enough to stop a beta particle. Gamma, though, gamma penetrate very far. So gamma, you need, depends on how energetic, generally speaking, about a foot of lead or 10 meters of concrete. So you need a lot of matter to stop gamma particles. I know I keep on using the particle because photons have wave particle duality. So I use rays and particles interchangeably. Same thing with alpha rays. You can call them rays because they do have a de Broglie wavelength. So that's one thing. That's a bad habit with nuclear stuff, is that nuclear scientists oftentimes use rays and particles interchangeably. Also, mass and energy can be used interchangeably frequently, because mass and energy are related by E = mc². So you can, sometimes a bad habit is you give mass in terms of energy. So, but gamma rays can go pretty far. It's hard to stop those. And but they exist very frequently, and basically for any nuclear equation has them. And they oftentimes, though, for the gamma, it's not even included, because it's just whenever there's a nuclear event, there's a gamma ray. So oftentimes it's not even included in the nuclear equation. So alpha is very easy. Okay, blocked by skin or a sheet of paper. Yes, it's very easy to block alpha particles. At the same time, though, so alpha sources are very safe outside of your body. So when it comes to, besides with radiation, there's physiological damage. Alpha sources are extremely damaging inside the body. So of course, so look at an alpha particle versus a beta particle. Beta particle is an electron. Alpha particle is a helium nucleus. So, and has 4 atomic mass units. So an alpha particle, in terms of mass, has about 8,000 times as much mass as a beta particle electron. So because of that, so 8,000 times as much mass, and if you know your physics, mass times velocity is momentum. That means that the alpha particles And this is an old reference, but it's like a pinball. Like if you ever had the old pinball machines when you have the ball goes pew, 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 all inside. It's important to say that pew, 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 pew too. So when you have an alpha particle, let's say that you have like an alpha decay happens inside the cell, and what's going to happen, that alpha particle is going to slam against the cell membrane. It's going to go and hit a mitochondria, it's going to jump to the nucleus. It's going to jump around the nucleus, break some DNA. It's going to leave the nucleus, and it's going to hit another mitochondria, and that's going to blow a hole in the cell membrane of the cell. It's going to be flying all over, causes massive damage inside the body. So outside the body, you hit me with a bunch of alpha particles, like, meh, no big deal. I don't care. Suddenly you have inside your body, you have an alpha source, then it causes some major damage, major damage. And that's for things like if you breathe in, say like radon, and that's in your lungs, and then alpha decay happens, that's going to cause some major damage to your lung tissue. So that's the reason why. And we don't have to worry about radon too much here in Hawaii, because we don't have any uranium in our soil. So we don't really have that much radon around. So actually the background radiation here in Hawaii, at least terrestrial source, is very, very low. So other places that have uranium in the soil, it's much higher. So on the mainland, like in the Midwest, and like I grew up in Ohio, and radon's heavy. It tends to collect in basements of houses. So you have to vent the basement of your house if you live in an area like that. And it's because radon will collect there, and it can cause cancer because of the cell damage. And how does cancer happen? Well, if you damage the DNA and the DNA is repaired incorrectly, then it can form a cancer cell. So, but in generally speaking, what does radiation do? It just causes damage. So it's not like it gives you superpowers. Radiation burns, a sunburn is a radiation burn. So you can get sunburns from like a first degree radiation burn is a first degree sunburn kind of thing. Like I don't know if you watched on HBO the series, the miniseries Chernobyl, and they're the people that looked. One of the guys went and climbed the tower and looked into the exposed core, and when he came down, his face was all red. That's because he just got a radiation burn from it. So that was pretty accurate. Not everything in that show was accurate, but that was accurate. The radiation burn from that. So okay, so that's alpha decay. So alpha decay is a helium nucleus, and then beta decay, and a neutron, a free neutron. You do not find free neutrons. Neutrons actually beta decay into protons and electrons. So also tells you something about a neutron. Neutron is slightly more massive than a proton. So the mass of a neutron is slightly higher than that of a proton. So and aforementioned beta, you need a thin sheet emitter. Oh, I didn't say that. Block of wood. So of course it depends on how many beta particles. So a little like so even leaded glass, like so someone like the crystal glass, that blocks beta particles. Block of wood, so it's pretty easy to contain beta. It just depends on the beta source though. Depends on all, so different beta particles, some have more energy than others. So some of them are stopped by air. So and they only go like an inch in air. Some go a little further. It depends on what the source of radiation is. And there's other ways of decay. There's a positron emission. So a proton, for instance, can turn into a neutron and can turn into a positron. So I already talked a little bit about antimatter. Here's a positron. A positron is it has a charge of +1 and a mass of 0. Well, it's negligible compared to a proton or a neutron. So that is a positron emission. And so the other thing about positrons are they find electrons and then they annihilate each other. And it's really easy to tell if there isn't a positron emission because the gamma ray is a specific energy. So you can find positrons very, very quickly. It's very easy to find positrons. And and actually even very similar to the positron emission, you have electron capture. You might also see this called K capture. Some places call it K capture or Kern capture, because I think that means first in German. So a lot of chemistry use German. So to study chemistry, like my father is a chemist, and he had to learn German, just like how a lot of places, like most of science is done in English today. So German used to be the language of chemistry, and a lot of names were German, and not just, well, we had a switch after World War II, right? So related to electron capture being Kern capture, like you ever wondered why I'm gonna get an EKG? And I'm like, what is an EKG? It's an electrocardiogram, but why isn't it an ECG? And they actually, if you talk to people now, they say ECGs. EKG is the electrocardiogram in German. So some of the words we still use today have German roots. So although one of the sources of English is German, so English is a weird language, so it doesn't bother us too much because of all the sources of our language. But electron capture, but I mean, sorry, coming back to the aside, if you see K capture or Kern capture, it means electron capture. And what is electron capture? The nucleus will absorb, typically in the 1s orbital, proton will absorb an electron and turn it into a neutron. Now, if you also remember, I don't if I mentioned, well, I did mention this in Gen Chem 1, electrons can exist in the nucleus, and do. So there is electron density in the nucleus of an atom. And especially with the 1s orbital. So if you have a more massive atom with a bigger, more positive charges, the 1s orbital is going to shrink in size, and you're going to have more electron density inside the nucleus of the atom. And then the proton can do an operation such that it absorbs one of the electrons from the 1s orbital and then turns into a neutron. So that's another way that you can have nuclear decay. So here is the summary of nuclear decay. So an alpha decay mode alpha, you have the parent nuclide, and it gives a daughter nuclide, and it releases a helium nucleus, helium-4 specifically, an alpha particle. And what happens is that the total mass in alpha decay, the total mass of the parent decreases by 4, and the charge decreases by 2. And a very common one, for instance, is uranium-238 decaying down to 234 thorium and an alpha particle. So a couple other sides from this. So if you wondered where helium comes from, much of the helium on Earth comes from alpha decay. So you find, depending on the region, some regions have more, but you find helium in natural gas, and you can isolate the helium, and that's how we isolated the helium in the United States. We generated a lot of helium back in the day, and actually our helium source of helium. This is something worrying scientists right now. Is our helium stockpiles. They've gone way down. And well, if you want a bit of history, we actually, in the United States, we stockpiled helium as a strategic weapon because we would use it to make blimps. And blimps were important because of you would float a blimp above a flotilla of ships. And for diesel submarines, if they attacked the flotilla, the blimp could fall along the sub. And when the subs surfaced to recharge its battery, the blimp could bomb the sub and sink the sub. So of course, with nuclear subs, we don't really need that anymore. So we just kind of got rid of our helium stockpiles, and lots of places use helium other than like both for scientific research. We can use different techniques can use helium, and the amount of helium right now is greatly depleted in part because the stockpile just went to almost nothing. Right? I mean, we use helium to for balloons, for instance, for party balloons. So it's in a way it's a waste. Okay, but so that's if you're wondering where the helium from the Earth comes from, it comes from alpha decay. So then we can also have beta decay, and a beta decay, a neutron turns into a proton and an electron, and what happens? The mass doesn't change that much at all, but the charge of the nucleus increases by 1 because a neutron turns into a proton. And also you can have excited state. So just like a excited state electron can go to a lower energy electron in atoms, same thing for nuclei. You can have excited nuclei going to a lower energy nuclei, and it releases a gamma particle or gamma ray. And whenever there is a nuclear transition, a gamma ray happens. So later on, we'll talk about imaging. And so a very common form of imaging uses technetium. And that has a 6-hour half-life, and it releases an excited nuclei, or not nuclei, yeah, excited nucleus, and it releases gamma rays. So I've had 2 bouts of nuclear medicine using those. So we can talk about it next time. And then positron emission. So positron emission, you have the parent, the daughter nuclei, and a positron. And what happens is the atomic number decreases by 1. So there's an example there: phosphorus 30 turning to silicon plus a positron. And electron capture, you have so the parent nucleide absorbs an electron and it forms a daughter, and then you have the decrease as well, of -1. So what's the difference between those two? Well, among other things, we know that a positron is formed because of the very specific gamma ray that's coming off. So whenever you have a new decay route, whenever you have a new state, you have a new energy of gamma coming off. So they're all unique for each specific nucleide. And for the positrons, you're going to see a very steady type of gamma coming off. So that's why we give it the different category. Although the effect is the same, but the energy fits the gamma ray coming off is very, very consistent with positron emission. So if you wonder why we have 2 different decay routes for that. So, okay, and sorry for time. So this chart here, we have this number of neutrons. So if you look at the y-axis, this is the number of neutrons, and the x-axis is the number of protons. And I know I mentioned this before, but I said, well, you have the nuclear strong force, the nuclear weak force, and the neutrons also have the nuclear strong force. So as you have a more positive center, you need to have more and more neutrons. And you can see that this curve kind of goes up this way. So the red line here is the x equals y. So that's the number of protons equals the number of neutrons, but as you get heavier, it curves upward. Why is that? Because you need more strong force to overcome the positive electrostatic force. And then here are the stable nuclei. So the stable ones are the green ones on this, and then you have the radioactive ones in yellow. So you can have unstable nuclei, and they have various degrees of stability. Some last for billions of years, like uranium. Some last for milliseconds, so like francium. So it just depends. It depends on the conditions. And so like carbon-12, for instance, so you see your carbon-12, you have same number of protons as the number of neutrons. For zirconium, you have 1.5 times, and then mercury, I'm sorry, 1.25 times, and then mercury, you have 1.5 times. So it's as you get more and more massive or bigger nucleus, you need more neutrons. So, and just like for chemistry, so there are magic numbers. So let me show you a periodic table. Here is a periodic table. And we have numbers of electrons that are very stable. We have 2, 10, 18, 36, 54, 86, and not listed, 118. So if you have that number of electrons, you have a very stable electron configuration. Same thing for nuclei, but those numbers are 2, 8, 20, 28, 50, 82, 126. So those numbers are very, very stable for nuclear things, for nuclei. Having that number of protons or neutrons. Of that, the most stable is 28. So 28 is the more important one, and that's also the reason why some stars explode. So that's the reason for type 2A supernovas. But I'll get to that. Or do I? Okay, I can talk about that next time. All right, so let's do some nuclear decays. So beta K and berkelium 249. So and so how would do this? You'd write berkelium. Let me make my pen smaller. And 249. So that would be 249 berkelium. I mean, I know I have the cheat sheet on the right. I can look at this. But let's say I want to do this for, if I didn't know it was berkelium. Now I have to go and I have to find berkelium on the periodic table. So here is berkelium. And berkelium is atomic number 97. So it's 97 berkelium, and it beta decays. So we know we're going to have something, and it's going to increase by 1, and we're going to keep, we're going to keep the same mass number, 249, and you're going to form a beta particle. So that's the beta particle. Is an electron. It's a beta particle, but what is the symbol for the next one? So we have to go back to the periodic table. It's going to move to the right one. It's element number 98, and element number 98 is californium. So this is going to be californium. So that's how you figure out these. And if you also hadn't noticed, also where I went to school, you know, can you guess where they found berkelium and californium? So many of the, at least the the transuranic elements were discovered in Berkeley, California. So if you wonder where some of the names there came from, some of the elements, I guess we can talk about this a little later, but we discovered them other ways. We actually found some of them from nuclear bombs, like doing the hydrogen bombs. We found out like, oh, we've made other stuff. Cool. So that's how you do. So recap with this one, beta decay of berkelium-249. So you find berkelium on the periodic table, it's 97 protons, and it's already mentioned 249. So beta decay means that we're not going to change the total number of the total mass of the nucleons, but we are going to increase the atomic number by 1. And so also add the beta particle, the beta electron, and then you have to figure out what the symbol is, and then you look at the periodic table. +1 from berkelium is California. So questions on how to do this? And it's balanced because the top numbers equal the bottom numbers. So 249 equals 249 plus 0. Bottom number is 97 equals 98 minus 1. So top and the bottom have to equal. Questions with this one? Okay, now we have positron emission of oxygen 15, and positron emission means that we are going to decrease the charge by 1, but the mass by 0. So positron emission, so when we do this for oxygen, so we're going to have 15, oxygen is 8, oxygen, it's going to go to, let's see here, it's going to keep the same mass, but it's going to decrease by 1. And then we're going to have a positron. So it's going to be 0 plus 1 for the positron. So we have to then go to the periodic table and figure out what element has 7 protons, and it's nitrogen. So, and it's just that one I have memorized. So if you go back to the periodic table, so here's oxygen, 8 protons, and it turns into nitrogen. And remember that with different with chemical reactions, the nuclei, the protons remain the same. The electrons will transfers though, but for nuclear reactions, you can change the number of protons and neutrons. So this is the case that you can change them. And then last one, electron capture in iodine. So it's going to be similar to the positron. So you're going to have so 111 iodine. Actually, maybe iodine's purple. I'll change this to iodine color-ish. 111 iodine, and you're going to have electron capture, 0 minus 1 electron. And I don't know the atomic number of iodine off the top of my head, so embarrassingly, I probably should know. 53. Okay, so go to the periodic table. It's 53. Oh, I guess I could have looked down there. I could have lied to you and say I did know it. It's also right there. So electron capture, so that means you're going to form, it's going to be 111, and it's going to be 52. And what is that? I'm going to cheat and look, and I can see it's tellurium. So same idea with the periodic table. It's going to jump over to 1, the tellurium with 52 positive charges. So hopefully you can see this is easy. Balancing nuclear equations is very easy. And it sounds daunting, right? You're like, I'm studying nuclear science. Nuclear science is hard. No, it's not. It's much easier. Chemistry is way harder than nuclear science. So, I mean, the math is the actual studying of nuclear science can be really difficult because trying to get the materials and isolating them, and they can be, I mean, the radioactive is dangerous and they can be toxic. And doing experiments with them can be very, very difficult. But like the problems, like the schoolwork problems are quite simple. Actually, just top numbers and the bottom numbers on both sides of the equation has to equal. So questions with this one so far? All right, so how do we detect radioactivity? So detecting radiation is one thing. So one of the ways you can do it is a film badge. And unfortunately, there was, gosh, what is that? That is Dr. No. That's the James Bond film. If you've ever seen it, James Bond, one of the things he does, he sneaks into Dr. No's compound and says, like, are you wearing your radiation shield? And he was saying, you're checking your radiation shields. The film badges, if you, they're about 3 inches long and 2 inches wide, and they're pretty thin, but you can, that's what they're typically sized. And you can usually wear them either on your chest or on your hip. And they're not shields. That's just a James Bond movie misnomer. I don't know. Has anyone seen Dr. No, or is this just, or no one likes James Bond here, or at least the old James Bonds? But a lot of people thought that the film badges were actually, they shielded you from radiation from that movie, but it's wrong. They don't shield you from anything. The film badges, though, they detect. They're very good at detecting. They detect long-term doses. So people that work around radiation have to wear the film badges, like people that work in X-rays, for instance. The people that like the X-ray technicians, like if you ever get your chest X-rayed or your arm X-rayed or something like that, the technicians should be wearing film badges, and they're usually on their chest or their hip, is typical. And sometimes people that work in the glove boxes. So if you have a glove box and you manipulate things, you can wear rings that have film badges on it, so you can monitor the dose of radiation you get to your hands. So the film badge, like I said, that's the long term. And then when you get the film developed, it can tell you how much radiation you've had over a long period of time. And there's also a Geiger-Miller counter. We also typically refer just as a Geiger counter. The way a Geiger counter works, so here is an image. The Geiger counters, they have a tube, and in the tube there's argon gas. It can be any like usually noble gas. It's usually argon. So in a sealed tube, you have argon gas, and then you have a wire. And the idea is when you have a gamma particle comes through, so a gamma particle just flies through, and what does it do? So gamma rays are known as ionizing radiation. So what does a jumping bean do? It jumps, right? So what does a kicking mule do? It kicks. What does ionizing radiation do? It ionizes. What does it mean to ionize? It means that you kick electrons off. So the argon atoms, they get hit by a gamma. The gamma comes in, and then the electron pew, comes off. So the electron flies off. I know I'm kind of making it overly dramatic there, but the electron flies off of the argon atom. And then so you get these negative electrons coming off, and they go towards the cathode, and then the positive argon ions go towards the anode. And as this happens, you get a signal. It gives a signal, and then the signal can turn into numbers and or clicks. So if you are using a Geiger counter, and whenever I use one, I always put it on the click noise, and you go around, you can find radioactivity very, very quickly because it does a kind of thing. So I have my own Geiger counter, and I can talk about it a little bit next or on Wednesday, but they fed me a radioactive sandwich once because they were studying my how fast my stomach was emptying, and when I got home from the hospital, I took my Geiger counter and I put it in my gut or in my stomach. And it was really, it was like really strong, well, actually, no, it emptied out of my stomach, but I could find my colon real easily because of the, where the radiation was, like I didn't have any in my chest, but I had it here, and, I could tell also, after it expelled, it was, I was no longer radioactive. So real easy to find the radiation, like I said. So that's a Geiger counter. So Geiger counters work by ionizing a gas and seeing the signal from it. Then there's also scintillation. These are oftentimes used for continuous radiation. You can use typically there's sodium iodide or cesium iodide, and when gamma rays hit this, they flash, it makes ultraviolet light, and then you can detect the ultraviolet light from the scintillation detector, or also from other types of radioactivity, things like like beta. You get the UV light, and then you detect the UV light. So scintillation detectors are actually detecting ultraviolet light by some means. So, but those are our primary ways of detecting radiation. So how are we doing for time? And I'm looking at this. I don't think I'm gonna have time to go over this. So what do I can, okay, I don't have time for that either. So I don't want to start the next problem is pretty complicated, and I don't want to just blow through it just for the sake of time. Does anybody have any questions about nuclear chemistry so far, though? No, no one has any questions. Well, I'll give you a preview. I guess I do have this amount of time. If you look at the curve of binding energy here, so I'm sure you've seen this equation before. You're probably familiar with that equation. E equals mc squared. Energy is equal to mass times the speed of light squared. This is actually an approximation. It works pretty well under most circumstances, but that's actually an approximation. It uses some of the like the exasmall approximations depending on the circumstance, but energy is approximately equal to mass times the speed of light squared. And when we coming up, we'll talk about nuclear reactions. And also, if you look at this chart here, we have the binding energy per nucleon. So how much mass there, well, I guess the other way around. As things form, as we form the elements, so you start with hydrogen, this is a proton, and helium is going to have protons and neutrons. So as you go further along the periodic table, there are protons and neutrons joining together, and it gets to a point, well, actually the general curve is as you go from left to right, there's a maximum. So when you form heavier and heavier nuclei, the amount of matter, so the energy, the amount of matter actually in the nucleus decreases. So as these protons and neutrons form these elements, the amount of matter in them decreases and it releases energy. And we have the maximum actually for the most stable elements in terms of nuclear is, in terms of radioactivity and nuclear chemistry, is iron, specifically iron 56. So, there's a 50, wait a second. It would be, yeah. So it's iron, and then after iron, actually, the amount of energy goes down. So going down that way, and but if you look at nuclear reactions, so when you fuse things together, like in stars, it takes going from hydrogen on up to iron that's exothermic, and the other way around, it's exothermic for nuclear fission. And this is important. I guess I don't have much time. I can talk about it again. This iron being the most stable is actually one of the reasons why we have a specific type of supernova. It's a type 2A supernova, and it's when a star, which has to be about 3 times or more as massive as the sun. The sun will never explode in this way, but other stars that are 3 times as massive or more, they have enough gravity such that they're able to form iron. And so once though a star starts generating iron, the nuclear fusion of iron is endothermic. And so you have, and stars are plasma or gas, obey the gas laws. What happens when you decrease the temperature of a gas? It shrinks, the volume goes down. And so if there's enough iron in the core of a star, and then there's enough pressure such that it forms nuclear reactions, the core of the star can shrink quickly, and the implosion can cause a shockwave explosion. And that's essentially how a type 2A supernova works. So, but we can talk about, I know I'm jumping with that, but that's a preview. I'll talk about it more in depth later, but that's a preview of what we talk about on Wednesday. So any questions for the last minute of class? No questions. All right. You have a question? Yeah. Okay. We have a class is over, but I will continue recording. So you can leave though. Anyways, go ahead. Dark energy. Yeah.
Thank you.
Okay, so question, if dark energy is in fact real, how does that affect particles? And I can tell you with absolute certainty, I have no idea. So we don't know what it is, and we don't know how it would interact with other things. It seems to work on the long scale of the universe. And I mean, I couldn't even begin to speculate. I have no idea. We have no idea. People have ideas. Most of the ideas have to do with gravity, though, that we don't understand, that we just don't understand gravity, or we don't understand space-time. So, but the problem is that we don't have a very good way to connect that to small things like particles. So that's our physics hasn't gone full circle yet. So that's where we might see a connection, but we don't know. Like I said, it's no idea. So sorry to give you an answer where it's absolutely